this video series, we'll be covering the CBSE Mathematics curriculum for Class 10. Let us begin with the first chapter, Real Numbers. We'll be covering an overall summary of the chapter and we'll also solve previously asked questions. According to the syllabus, Real Numbers has been divided into 4 sections. The first section is Euclid's division lemma. This portion has been excluded for the current academic year. Therefore, we will not be covering the same in our discussion. The second topic is a theorem called Fundamental Theorem of Arithmetic. We'll understand the theorem. We'll also see how it is applied to find the HCF and LCM of numbers, and we'll also see the relationship between product of two numbers and product of their HCF and LCM. The third topic is proofs of irrationality of root 2, root 3 and root 5. Here we'll cover the method proof by contradiction and we'll also see a theorem which is used for the proofs. The final section is on decimal representation of rational numbers, which is either terminating or non-terminating recurring. So now let us begin with the first topic, Fundamental Theorem of Arithmetic. The theorem states that every composite number can be expressed as a product of primes, which is also called the factorization or prime factorization, and this factorization is unique apart from the order in which the prime numbers occur. So the theorem states that every composite number can be expressed as a product of primes. This factorization is unique apart from the order in which the factors occur. Let us understand this with the help of an example. Let us consider the number 210. 210 is a composite number. Now we factorize 210 to express it as product of primes. So we start with the smallest prime number 2. 2 divides 210, we get 105. 2 will not divide 105, so we move on to the next prime number, which is 3. 3 will divide 105, 35. Now 3 will not divide 35, so let's move on to the next prime number, which is 5. 5 divides 35, 7, and here 7 is a prime number, so we cannot factorize this further. So now we've arrived at the prime factorization or the product of primes for 210. 2 into 3 into 5 into 7. So we've covered the first part of the theorem, that is, we've expressed the composite number 210 as product of primes. Now what does the theorem suggest? That this combination of prime numbers is unique to the composite number 210. So if you multiply these numbers 2, 3, 5 and 7 in any order, it will always give you 210, and 210 is the only number which will have 2, 3, 5 and 7 as its only prime factors. Now let us try rearranging the factors. Let's rearrange it as 7 into 5 into 3 into 2, which is equal to 35 into 3 into 2, which is equal to 105 into 2 is equal to 210. So irrespective of the order in which you consider the prime factors, you would always get the composite number which it represents. So now we've understood the theorem. What does it say? It says that any composite number can be expressed as a product of primes which is unique to it and apart from the order in which the factors occur. Now let us use this theorem or the product of primes to find HCF and LCM of two numbers. Let us consider the numbers 30. Number 30 is a composite number. It can be expressed as product of prime numbers 2 into 3 into 5. Let's consider another number 12, which can be expressed as 2 into 3, which is 2 raised to 2 into 3. So we've got two composite numbers and we've expressed them as product of primes. Now, to find the HCF or the highest common factor, what we need to see is consider the product of primes, and based on which you choose the product of smallest powers of common factors. Okay, among the two, you will consider the product of smallest powers of common factors. So what are the common factors here? 2 is common, 3 is common, 5 is not common. So we have 2 and 3. Now we have to consider the smaller of the two powers. So here it's 2 raised to 1, here it's 2 raised to 2. So 2 raised to 1, 3 raised to 1, 3 raised to 1, so 3 raised to 1. So we get 2 into 3, which is 6. So how do we find the HCF? You first express the numbers as product of primes. Based on the product of primes, you choose the product of smallest powers of only common factors. So the common factors here are 2 and 3, and the smallest power of 2 is 1, 3 is also 1. So we get 2 into 3 is equal to 6. Now we'll see how we can find the LCM. LCM is the, again, product of. So similar to HCF, this is also product of, but here we'll choose the greatest power. So for HCF, we chose the smallest power. Here we'll choose the greatest power of each factor. So for HCF, we had chosen only the common factors, but here we'll choose each factor. So here we have 3 factors, 2, 3 and 5, even though 5 is not common to both. 2 into 3 into 5. And the powers, we have to choose the greatest power. So power of 2 is 1 here, it's 2 here, so 2, 3, 1 here, so 3, 5, 1 here, so 1, which is equal to 60. So what did we do? We expressed the numbers as product of primes. We chose all the factors, we chose the product of all the factors, and we chose the greatest of the power. Comparatively, greater power is chosen for the product. So we've arrived at the LCM, which is 60. Now, from these numbers, we can arrive at an interesting result. Let us find the product of the two numbers, that is 30 into 12, which is equal to 360. Let us also find the product of the HCF and LCM, which is 6 into 60, again 360. So now we see that the product of the two numbers is same as the product of the HCF and LCM. This is true for all positive integers. So for any two positive integers, their product is equal to product of their HCF and LCM. So in fundamental theorem of arithmetic, we've understood what fundamental theorem of arithmetic is. We've seen how product of primes is used to find the HCF and LCM of two numbers, and we've also seen the result which states that product of two numbers is equal to product of their HCF and LCM. Now let's move on to the next section, which is proofs of irrationality of root 2, root 3 and root 5. Before going into the topic, let's first understand what is irrationality, what are rational and irrational numbers, and why root 2, root 3 and root 5 are irrational numbers. So first, let's understand what are rational numbers. Any number which can be expressed in the form P by Q, where P and Q are integers and Q not equal to 0 is a rational number. So any number which can be expressed in the form P by Q, where P and Q are integers and Q not equal to 0 is a rational number. So it is basically a fraction involving integers. Let us look at a few examples. 3 by 2 is a rational number. P by Q, 3 and 2 are integers. Minus 2 by 7 is also a rational number. Minus 2 is an integer, 7 is an integer. What about the number 5? 5 is an integer, but it is also a rational number because it can be expressed as 5 by 1, which is again in the form P by Q. Even decimal numbers like say 1.5 is a rational number because it can be expressed as 3 by 2. So any number which can be expressed in the form P by Q, where P and Q are integers and Q not equal to 0 is a rational number. So what is an irrational number? Any number which cannot be expressed in the form P by Q is an irrational number. The irrational numbers that we are dealing with here are root 2, which is equal to 1.414, so on. Root 3, which is equal to 1.732, so on. Root 5, which is equal to 2.236, and so on. So here you can see that all irrational numbers have non-terminating repeating decimals. This is the feature of irrational numbers. A number is said to be irrational if its decimal expansion is non-terminating repeating. That is why root 2, root 3 and root 5 are all irrational numbers. The most popular irrational number is pi. Pi is 3.14159, so on. Pi is also an irrational number because it is non-terminating repeating. So we've seen rational numbers and irrational numbers. The difference is rational numbers can be expressed in P by Q form and irrational numbers cannot be expressed in P by Q form. When you express it in the decimal representation, irrational numbers will have non-terminating, non-repeating decimals. So now that we've understood why root 2, root 3 and root 5 are irrational, let us move on to the proofs of irrationality of root 2, root 3 and root 5. The method used for the proof is called proof by contradiction. What is a contradiction? Contradiction means the opposite or a counter statement. In proof by contradiction, suppose we are given a statement to prove. We would first assume that the statement is not true. We will assume that the statement is not true. Then we will make logical deductions or apply logical rules to arrive at the result which will prove assumption that we made initially is wrong, thereby proving that the statement is indeed true. So we first assume that the statement is not true, then we perform logical deductions and arrive at a result which proves our assumption wrong, and thereby proving that the statement is indeed true. What is our statement here? That root 2, root 3 and root 5 are irrational. So our assumption would be the opposite, which is root 2, root 3, root 5 are rational. So this will be our assumption, and finally after the proof we'll realize that our assumption was wrong, and thereby proving that root 2, root 3 and root 5 are irrational. So this is the technique used for proving the irrationality of root 2, root 3 and root 5. In addition to proof by contradiction, there is one more theorem which is a prerequisite for this proof. The theorem states that for a prime number p and a positive integer a, if p divides a square, then p divides a. So for a prime number p and a positive integer a, if p divides a square, then p divides a. Let us take an example of prime number 3 and a as 9. So we know that 3 divides 9 square, which is 81. So 3 divides 81, and 3 also divides a, which is 3 divides 9. So this is true for the prime number 3, and this is true for any prime number for that matter. So if p divides a square, then p divides a. So now let's move on to the next section, which is decimal representation of rational numbers. So in the previous section, while we were discussing irrational numbers, I had mentioned that decimal representation of irrational numbers is always non-terminating recurring. So what are terminating and non-terminating decimals? Terminating have fixed number of digits after the decimal point. Terminating decimals have fixed number of digits after the decimal point, whereas non-terminating has infinite digits after the decimal point. So this is the difference between terminating and non-terminating. Terminating, which ends or which has fixed number of digits after the decimal point, and non-terminating has infinite number of digits after the decimal point. Now, we've also seen something called non-terminating recurring decimal. So non-terminating recurring decimals are those which show a particular pattern or which repeat in a particular pattern infinitely. So it is non-terminating, but it's recurring, or there is a repetition of a particular pattern of digits. So while irrational numbers have non-terminating, non-recurring or non-repeating decimal representation, rational numbers have either terminating or non-terminating recurring decimal representation. Okay, so rational numbers have either terminating or non-terminating recurring decimal representation. So now let's see a few examples. 3 by 2 is equal to, now this is a rational number because it's in the p by q form. 3 and 2 are integers. Now when I express it in the decimal form, it becomes 1.5, which has fixed number of digits after the decimal point. Therefore, it's a terminating decimal. Now the next number, let's say 2 by 5. 2 by 5 is equal to 0.4 in the decimal form, which is also terminating with fixed number of digits after the decimal point. Let's consider one more example, say 7 by 10 is equal to 0.7, which is also a terminating decimal. Now let's look at another example, which is 8 by 3. Now 8 by 3 in its decimal form would be 2.666. Here you can see it's a non-terminating recurring decimal. Let's take another example, say 5 by 7. Let's divide 5 by 7. 7 goes 7 times and I get a remainder 1. 7 ones are 7. I get remainder 3. 4s are 28. Remainder 2. 7 2s are 14. Remainder 6. 7 8s are 56. 4. 7 5s are 35. So we've arrived at 5 again, which means this pattern will repeat forever. This is also therefore a non-terminating repeating decimal. So based on these patterns, we can infer a result. When you express a rational number in its p by q form, and if its denominator q is expressed as product of primes, or the prime factorization of the denominator has only 2 and 5, either 2 or 5, it only has powers of 2 and 5, then it is a terminating decimal representation. So if you express a rational number in its p by q form and you find the prime factorization of q, if it contains only powers of 2 and 5, then it is a terminating decimal. Otherwise, that is, if it contains any number other than 2 and 5 in its prime factorization, such as 3 or 7, then it will have a non-terminating recurring decimal. So first, when you are given a number, if you are to check whether it will have a terminating or a non-terminating recurring decimal representation, first express it in the p by q form, check the q, check the prime factorization of q. If it has only powers of 2 and 5, it will be terminating. If it has any other prime factor other than 2 and 5 in its denominator, then it will have non-terminating recurring decimal representation. So formally, the rule can be defined as follows. If a rational number is expressed in the p by q form and the q, or the denominator, is prime factorized, okay, the prime factorization of q has only powers of 2 and 5 is equal to 2 raised to n, 5 raised to m, where n and m are non-negative. Why? Because it can be 0. So non-negative integers, then the rational number will have terminating decimal representation. So first you express the rational number in p by q form. The denominator q has to be prime factorized, and if its prime factorization contains only powers of 2 and 5, where you can either have only 2, you can even have only 5, and you can have both. So anything other than 2 and 5, for example 3 or 7, you will get a non-terminating recurring decimal representation. So this is the rule to find if a rational number will have terminating or a non-terminating recurring decimal representation. Now that we've covered the summary of the chapter, let us solve previous year questions which will be covered in the upcoming videos.